In this video, we're going to analyze acid-base reactions. So the first thing we're going to do is define what an acid-base reaction is. We're going to learn how to write the molecular equation, the ionic equation, and the net ionic equation for a given acid-base reaction. So of course, an acid-base reaction is a reaction between an acid and a base. But it's important to note that the acid may be strong or weak, so we have to pay attention to that. And the base may also be a strong or weak base, so it's important that you familiarize yourself with the different types of strong and weak acids and bases. An acid-base reaction is also called a neutralization reaction because the acid and base neutralize each other, and we generally form water. And so the products are generally water and some ionic compound that we call a salt. Not always, but generally. And the acid-base reactions follow the same general pattern as a double replacement reaction. So when we talk about strong acids and weak acids, again, it's important that you familiarize yourself with the few strong acids that we study, and then any other acid that you encounter would, of course, most likely be a weak acid. So here's an example of an acid-base neutralization reaction. Here we have hydrochloric acid, a strong acid, reacting with sodium hydroxide, a strong base, and we produce water, which is a liquid, and we produce, in this case, sodium chloride as our ionic compound. And so this would be what we call the molecular equation. Our complete balanced equation is called the molecular equation. So let's take a look at how to write a proper molecular equation for a neutralization reaction. Let's start by giving you these two products. Here we have hydrobromic acid and we have barium hydroxide. Pause the video for just a minute and see if you can predict the products of this reaction before we go over it. Okay, so when we react these two compounds, the acid and the base, we want to be able to predict the product. So there's a few steps that we want to follow. The first thing, in order to predict the products, we take only one of the first cation, in this case it would be H+, and we match it up with only one of the second anion, which would be our hydroxide. Now we have two hydroxides, but we only want to match one cation with one anion. So if we put a H+ and an OH-, we get HOH. Now the second step, we take one of the second cation, that would be our barium, and we pair it up with one of our second anion, that would be our bromide. And again, we always write the cation first, so this would be barium BaBr, or barium bromide would be our second product. So again, don't worry about writing the correct chemical formula, just match up the correct cation and anion first. The second step, now we want to be sure that we've got everything written correctly, all of our chemical formulas. And we do that by looking at the charges. So here, let's look at this first product. We have H+ and OH-. So those charges add up to 0. Over here we have barium. Barium has a +2 charge, and bromide has a -1 charge. So those are not paired up correctly. So in order to get them paired up correctly, we need 2 bromides for every 1 barium. Okay, so first step, pair them up, cation to anion. The second step, now we write the correct number based on their charges. Now that we've got the products written correctly, we can balance our equation. We see that this equation is not balanced because, for example, we have 2 bromides, and over here we have 1 bromide. Now notice that we've written HOH as H2O. Of course, HOH is more commonly written as H2O or water. So now we have to balance it. So in order to balance this equation, I would put a 2 here in front of my hydrobromic acid and a 2 in front of the water. Now everything should be balanced. So pause the video and convince yourself that this is indeed balanced. And there's one last step. We need to predict the solubilities of each of our products. So you notice water, well, that's a pure liquid, so we can put an L after that. And barium bromide, we need to consult our solubility table, and we would find that barium bromide is indeed soluble. So if it's soluble, we would put an AQ. If it's an insoluble salt, we would put an S for solid. So now we've written our correct molecular equation. We can move on and write our ionic equation. So again, here's the equation we've been working on. Our hydrobromic acid reacts with barium hydroxide to give us water and barium bromide. Everything's balanced. We have all the correct states. So to write our neutralization, our ionic equation for this neutralization reaction, we need to follow a couple of steps again. First step is write the correct balanced molecular equation. We did that. The second step, write any strong electrolytes. So be sure that you're familiar with what that term means. Write any strong electrolytes in their dissociated form. Strong electrolytes include soluble ionic compounds and strong acids. So be careful. Be sure that your acid is a strong acid and not a weak acid. And third, any compounds that are solid, liquid, gas, or weak electrolytes, we write in the undissociated form. So we don't write them separated into their ions. So let's take a look at this. Here's our molecular equation, and let's start here with HBr. That's a strong acid. We can look on our table and see that. So we're going to write it in its dissociated form. We have two HBr's, so we're going to get two H pluses plus two Br minuses. And again, put the charges and the phase after each thing. So pay careful attention to these details. Now, barium hydroxide, that is a soluble ionic compound. That's a strong base. So we write that dissociated. Ba2 plus, and we get 2 hydroxide. So be sure that you write the 2 in front of it, not as a subscript like that. That would be incorrect. So our barium hydroxide, we write dissociated. Now we move on to water. Water is a pure liquid. We do not write it in its dissociated form. Remember, compounds that are solid, liquid, gas, or weak acids are not written in their dissociated form. So we leave that as is. And barium bromide is soluble, and so again we write that in its dissociated form. And again, I want to draw your attention, we do not write Br little 2 minus, we write 2 Br minus, because barium bromide is composed of 3 ions, 1 barium and 2 bromides. So when it dissociates, it breaks into 1 barium and 2 bromides. Okay, so again, pay careful attention to that. So what we have here is our total ionic equation. Again, remember the charges, the phases, and be sure that this is balanced. You can check your work. So now we can move on and write our net ionic equation. So we have our molecular equation done. We have our ionic equation done. So let's look at the steps for writing a net ionic equation. This is, of course, basically just a simplified version of our ionic equation. And in the net ionic equation, we cross out any ions that are unreactive, that are the same on the left side as they are the right side of our equation. So the only things left in the equation are those that undergo some chemical change. They form an actual product that's a solid, liquid, or gas. The things that did not change, the things we crossed out, are called spectator ions. So be familiar with those terms. So let's take a look. Here's our molecular equation. We wrote the ionic equation, so again, be sure to study that. Now, pause the video and see if you can cross out the spectator ions and write the correct net ionic equation. Okay, so for the net ionic equation, here I've just rewritten the ionic equation, and if you notice, the bromide, we have 2 Br minuses here and 2 Br minuses here. The bromide did not undergo any chemical reaction. It's soluble on both sides, so we can cross that out. And also the barium ions did not react to form any products, so the barium ions would be considered spectator ions, so we cross those out. The H plus and OH minus did form a new substance, which is water, so we rewrite the equation without the spectator ions, and we have 2H plus 2OH minus yields 2H2O. Now we could simplify this by getting rid of the 2's and simplify it as you see here. So this would be our net ionic equation for our acid-base neutralization reaction. So let me have you try a couple. Here's a problem. Write the molecular, the ionic, and the net ionic equations for this reaction. Pause the video and give it a try. Okay, so first thing I notice is that I have a strong acid and I have a strong base here, lithium hydroxide. So I'm going to follow my rules. I'm going to take my H and pair it up with my OH minus, and I'm going to take one of my lithium and pair it up with one of my nitrates. Okay. Now I'm going to balance the charges, but these are already balanced. The lithium's +1, nitrate's a -1, and I'll rewrite the HOH as H2O. Now I predict the phases. My water's a liquid. Lithium nitrate is soluble. So now I have my complete molecular equation, and this is balanced. So now we can move on to write our ionic equation. Again, everything that is a strong acid or an ionic compound that's soluble, we write in the dissociated form. So please pay careful attention to how I've written it here and be sure you have it written very similar to what I have. Now we can cross out our spectator ions, which are the nitrate and the lithium ions, and we write what's left. In this case, it's going to be, again, H plus OH minus yields H2O. That's our net ionic equation. Let's try one more. Here's problem 2. Here we have an acid and a base. Now I want you to pay careful attention to this acid. Check to see if this is a strong acid. Okay, so pause the video and see if you can predict the molecular, ionic, and net ionic equations for this reaction. Okay, so here, again, we're going to write our molecular equation. We're going to pair up the H with the OH minus, and we're going to pair up the potassium with the nitrite. We'll get OH, HOH, or H2O, plus KNO2. Now we look at the charges, and we see that indeed everything is balanced. Our charges are all balanced. And so now we can look at the phases. Our HOH, or H2O, is going to be a liquid, and KOH, that's soluble. So this would be our complete molecular equation, and this is balanced. Now we write the ionic equation. Now remember, I told you to pay careful attention to the acid. This is a weak acid. Weak acids, we do not write in the dissociated form. Weak acids do not completely dissociate. They dissociate only a small extent. So we write HNO2, or nitrous acid. We write it in its undissociated form. The potassium hydroxide, however, is a soluble ionic compound, a strong base. So we write it as K plus OH minus. Water, we write undissociated as a pure liquid. And potassium nitrite, we write, again, in its dissociated form because it is soluble. So this, again, pay attention to the charges. Make sure everything is balanced. Be sure you have all the correct phases. Pay attention to the details. This would be our correct ionic equation. Now the net ionic equation. We cross out any of our spectator ions. That would be our potassiums. The nitrite you can't cancel because it's not dissociated over here. It is here. So it has undergone some change in this reaction. So the only thing we can cancel out is our potassium ions. And so we rewrite our net ionic equation without the spectator ions, and you can see that's what we have here. So again, it's very important that you pay careful attention to those acids and bases. Be sure that you have strong acids in order to write them dissociated, and if it's weak, write it in the undissociated form. So please be familiar with those steps and practice a few more of these to get comfortable with acid-base reactions.